What if everything we think we know about the universe is just the tip of the iceberg? Picture staring up at the night sky, feeling that familiar awe. But what if I told you the cosmos holds secrets so strange they defy logic itself? From black holes that might be gateways to other dimensions to the eerie possibility that our reality is just one layer of an infinite multiverse. Space isn't just vast, it's vibrating with mysteries that shake the very foundations of physics. Today, we're diving into 30 of the most mind-bending theories about the nature of space, ideas so wild they'll make you question whether we've even begun to scratch the surface of understanding our place in the universe. Think about this for a moment. What if time doesn't flow the way we experience it? What if the past, present, and future all exist simultaneously, like frames in a cosmic film reel? Or consider the haunting notion that dark matter, the invisible glue holding galaxies together, might be evidence of an entirely separate universe brushing against ours. These aren't just plot twists from a sci-fi novel. They're real hypotheses debated by brilliant minds, each one a puzzle piece in humanity's grand quest to decode the cosmos. And here's the thing, every time we think we've got space figured out, it throws us another curveball, leaving us equal parts humbled and electrified by the sheer audacity of the unknown. That's the thrill of exploring these theories. They're not just abstract ideas. They're invitations to wander the edges of human imagination, to dance with the possibilities that lurk beyond the limits of our telescopes and equations. Whether it's the chilling concept of false vacuum decay, where a single quantum fluctuation could rewrite the laws of physics in an instant, or the tantalizing idea that wormholes might stitch the fabric of space-time together like hidden shortcuts, each theory we'll uncover today is a reminder. The universe is far weirder, far more wondrous than we ever dared to dream. So buckle up. By the time we're done, you'll never look at the night sky the same way again. What if the world around us, the trees, the stars, even your own hands, isn't as three-dimensional as it seems? The holographic universe theory flips our understanding of reality on its head, proposing that everything we perceive might just be an incredibly detailed projection from a flat, two-dimensional surface at the edge of the cosmos. Imagine the universe as a cosmic movie screen with a vivid illusion of depth painted onto it. This isn't science fiction, it's a serious hypothesis backed by physicists like Leonard Susskind, who saw in the math a startling possibility. Our reality could be encoded on a distant boundary, like a hologram storing three-dimensional information on a two-dimensional sheet. At the heart of this idea is something called the AD/CFT correspondence, a mathematical bridge between two seemingly unrelated theories in physics. On one side, you have string theory playing out in a warped, higher-dimensional space. On the other, a simpler theory describing particles interacting on a flat surface. The discovery that these two wildly different frameworks could be equivalent was like finding a hidden dictionary between alien languages, one that suggests information about what happens inside a volume of space might be fully described by what's written on its outer shell. Think of it like a black hole. All the messy details of what falls in might not vanish, but instead get smeared across its event horizon, preserved like data etched onto a celestial hard drive. The implications are staggering. If the holographic principle holds, it could solve one of physics' biggest headaches, the black hole information paradox. When matter gets swallowed by a black hole, does it just disappear, violating the laws of quantum mechanics, or is that information somehow preserved? The holographic universe offers an elegant answer. It's never truly lost, just scrambled and encoded on the boundary, like a cosmic game of telephone played across dimensions. Even more mind-bending, this might mean that space itself, with all its vast emptiness, isn't fundamental but emerges from something deeper, like a 3D image rendered from a 2D code. So next time you reach out to touch something, ask yourself, are you feeling an object or just the universe's most breathtaking illusion? one of the most compelling pieces of evidence supporting the holographic universe theory comes from an unexpected place: black holes. When physicists calculated the entropy of these cosmic vacuum cleaners, they found something bizarre. The amount of disorder inside a black hole isn't proportional to its volume, as you'd expect, but to the area of its event horizon. It's as if all the information about what fell in got compressed into a two-dimensional surface, like a cosmic zip file. This discovery, made by Jacob Bekenstein and later refined by Stephen Hawking, became known as the holographic bound, a mathematical clue that the universe might store data like a hologram, with the real action happening not in the 3D space we perceive but on its outer edges. But what does this mean for us? If the holographic principle is true, it raises dizzying questions about free will and destiny. Imagine every moment of your life, every choice, every heartbeat already encoded on some distant cosmic boundary, playing out like a pre-recorded film. Are our decisions truly ours, or are we just reading lines from a script written in the fabric of space-time? Some philosophers argue this doesn't erase free will. It just redefines it, suggesting that even if reality is predetermined, our experience of making choices remains real and meaningful. Others see it as proof that consciousness itself might be part of the projection, a flickering shadow cast by deeper, unseen processes. The implications ripple beyond philosophy into the bedrock of physics. If space-time is emergent, not fundamental but cobbled together from quantum bits on a distant surface, it could reconcile Einstein's relativity with quantum mechanics, two theories currently at war. Picture it like pixels on a screen. Zoom in close enough, and the smooth image breaks into discrete dots. Similarly, the holographic universe suggests that the seamless fabric of space might pixelate at the tiniest scales, revealing a hidden code beneath. Experiments like the holometer at Fermilab are already hunting for this granularity, listening for spacetime's faint static, a potential whisper from the universe's ultimate hard drive. Here's where it gets even stranger. If our 3D world is a projection, could other layers of reality exist beyond it? Some theorists speculate that holography might open doors to parallel universes, each a different rendering of the same underlying data. It's like having multiple apps running on a single operating system, one cosmic source code generating infinite variations. Whether this theory holds or not, one thing's certain: the holographic principle has shattered the way we think about space, proving that sometimes the universe's deepest truths aren't hidden in the stars, but in the margins of the cosmic page. What if our universe is just one bubble in an endless cosmic froth, constantly multiplying in an ocean of unseen realities? Eternal inflation takes the already mind-bending concept of cosmic inflation, the idea that our universe expanded exponentially in its earliest moments, and dials it up to 11. Proposed by physicist Alan Guth in the 1980s, inflation wasn't just a one-time event in our past. Instead, it might be an unstoppable, eternal process, endlessly birthing new universes like bubbles in a boiling pot. Picture space itself as a seething cauldron where quantum fluctuations act as tiny sparks, each one igniting a new pocket of reality with its own unique laws of physics. Here's how it works. In the inflationary model, a peculiar kind of energy, the inflaton field, drives the rapid expansion of space, but this expansion isn't perfectly uniform. Tiny quantum jitters create random variations in the field, causing some regions to stop inflating while others keep stretching. The areas that settle down become stable universes like ours, while the rest continue ballooning outward, spawning even more bubbles in an infinite cascade. It's like a cosmic version of a chain reaction. One universe gives rise to countless others, each forever hidden from the next by the ever-expanding space between them. This raises a haunting question: why can't we see these other universes? The answer lies in the sheer speed of inflation. The space between bubbles stretches faster than light can cross it, meaning no signal, no particle, no possible observation could ever bridge the gap. It's as if we're on a raft drifting away from an endless shoreline of other rafts, each carrying its own version of reality, forever out of reach. Some of these universes might have stars and galaxies like ours. Others could be utterly alien, with different constants of nature, maybe even no atoms at all. The implications are staggering. Eternal inflation doesn't just suggest a multiverse, it demands one, turning the cosmos into a fractal labyrinth of possibilities. And while we'll likely never observe these sibling universes directly, their existence could solve one of physics' greatest mysteries: why our universe seems so finely tuned for life. If every possible combination of physical laws exists somewhere in the multiverse, it's no surprise we find ourselves in one of the rare bubbles where conditions are just right. Like winning the cosmic lottery without even buying a ticket. Yet for all its elegance, eternal inflation isn't without controversy. Some critics argue it's more metaphysics than physics, a theory so vast it can't be tested. Others see it as a necessary consequence of the math, a door we opened when we first glimpsed the quantum origins of our universe. Either way, one thing's certain: if true, our cosmos is far lonelier and far stranger than we ever imagined. Not just a universe, but a single note in an endless symphony of realities, playing forever in the dark. If string theory is correct, our universe might be just one accidental arrangement in a cosmic library of 10 to the power of 500 possible configurations. That's a 1 followed by 500 zeros, a number so vast it dwarfs the count of atoms in the observable universe. Each of these configurations represents a unique vacuum state, a self-contained set of physical laws where gravity might be stronger, particles heavier, or even the number of dimensions different. Some of these universes could be barren, lifeless voids, while others might flicker in and out of existence in the blink of an eye. But here's the twist: we find ourselves in one of the exceedingly rare versions where the numbers lined up just right for galaxies, planets, and life to emerge. This is the essence of the anthropic principle, the idea that our existence as observers necessarily shapes the kind of universe we're capable of perceiving. The anthropic principle comes in two flavors: weak and strong. The weak version is almost a tautology. If the universe weren't hospitable to life, we wouldn't be here to question it. But the strong version goes further, suggesting the universe might somehow be compelled to produce conscious observers, as if life were written into its foundational code. Critics argue this borders on teleology, a backward way of thinking where the outcome dictates the cause. Supporters counter that in a multiverse, the anthropic principle isn't mystical, it's statistical. With infinite cosmic dice rolls, it's inevitable that some universe would hit the jackpot. Enter Max Tegmark's multiverse classification system, which sorts these alternate realities into 4 distinct tiers. Level 1 is the simplest: universes like ours, endlessly repeating in an infinite expanse due to quantum randomness, where somewhere far beyond our cosmic horizon, an identical version of you might be reading these same words. Level 2 introduces bubble universes born from eternal inflation, each with its own physics, forever separated by expanding space. Level 3 is the quantum multiverse, where every possible outcome of every quantum event spawns a new branch of reality, meaning there's a version of history where you clicked away from this video, another where you rewound it, and another where dinosaurs never went extinct. But Tegmark's Level 4 is the wildest of all, universes governed by entirely different mathematical structures where the very concept of space-time might not apply. Here, the laws of physics aren't just shuffled but reinvented from scratch, birthing realities so alien we lack the vocabulary to describe them. Imagine a cosmos built not on equations of motion and energy, but on pure geometric symmetries or abstract logic gates, a universe where physics, as we know it, is just a quaint footnote in an infinitely stranger playbook. String theory's landscape and Tegmark's framework together paint a picture of reality far grander and far humbler than we ever imagined. our universe isn't the centerpiece of existence. It's a single snowflake in a blizzard of possibilities. And whether you find that thought exhilarating or unsettling, one thing's clear. In the multiverse, the only limit is the human mind's capacity to wonder. What if death isn't the end, but just a door you never walk through? Quantum immortality is one of the most unsettling ideas to emerge from the many worlds interpretation of quantum mechanics, suggesting your consciousness might always find a way to continue, no matter how unlikely the odds. Imagine a gruesome thought experiment. You're strapped into a device that measures the spin of an electron. If it lands one way, a gun fires. If it lands the other, nothing happens. Each time you pull the trigger, quantum randomness dictates the outcome, splitting reality into two branches, one where you die and one where you inexplicably survive. According to this theory, you would only ever experience the branches where you're alive, no matter how statistically improbable your survival becomes. This isn't just morbid speculation, it's rooted in the same math that underpins quantum mechanics. In the many worlds view, every possible outcome of a quantum event spawns a new timeline, meaning there's always a universe where the electron spin saves you, even if the odds are 1 in a billion. Your consciousness, like a cosmic hitchhiker, clings to the strand of reality where you persist, while countless other versions of you cease to exist. Proponents argue this isn't about cheating death, but about the nature of observation itself. If consciousness requires a living observer, then by definition, you can only ever witness the realities where you're alive. But here's the catch: quantum immortality isn't something you can test. For every person who miraculously survives a deadly scenario, there are infinitely more branches where they don't, and those versions aren't around to argue. Critics call it a tautology, a clever trick of logic that conflates perception with reality. After all, if you can't observe your own death, does that really mean it never happens? Some physicists dismiss it as philosophy masquerading as science, while others see it as an inevitable consequence of taking the many worlds interpretation seriously. The implications spiral into existential vertigo. If quantum immortality holds, could someone live for centuries through sheer luck, hopping between increasingly improbable timelines? And what about aging? Would consciousness eventually find itself trapped in a universe where biological limits are suspended? Or would it simply fade into a sea of branching possibilities? There are no clean answers, only the eerie realization that under this model, death might not be a fixed destination, but a horizon that forever recedes as you approach it. Perhaps the most haunting question isn't whether the theory's true, but what it reveals about our place in the cosmos. If reality is a labyrinth of forking paths, then every choice, every accident, every near miss isn't just a moment, it's a doorway. And while we'll never know for sure what lies on the other side of the ones we don't take, quantum immortality whispers a chilling possibility. Somewhere, in some branch of the multiverse, you already did. Now consider this: what if you're not a product of evolution, not even a human at all, but a fleeting flicker of self-awareness conjured into existence by pure cosmic chaos? This is the spine-chilling premise of the Boltzmann brain, a thought experiment so bizarre it makes the multiverse seem tame. Named after physicist Ludwig Boltzmann, who wrestled with the mysteries of entropy in the late 19th century, the theory suggests that in an infinite, randomly fluctuating universe, the most unlikely things become inevitable, including disembodied minds popping into existence fully formed, complete with false memories of a past that never was. At its core, the Boltzmann brain paradox is a battle against entropy, the universe's relentless slide toward disorder. Boltzmann realized that given enough time, even the most improbable states of order will briefly emerge from the chaos. Picture a box of gas. Left alone, its molecules will spread out evenly, but given trillions of years, they'll eventually randomly rearrange themselves into the shape of a snowflake, a smiley face, or even a functioning brain. Now scale that up to the entire cosmos. In an eternal, infinitely vast universe, there's a non-zero chance that quantum fluctuations could spontaneously assemble a conscious observer complete with fabricated sensory input out of the void. And here's the kicker: statistically, these freak accidents should vastly outnumber ordinary brains like ours, which evolved over billions of years. So why does reality feel so stable? This leads to the arrow of time paradox. We perceive time as flowing forward because entropy increases, eggs crack but don't uncrack, ice melts but doesn't refreeze. But if entropy dictates that disorder grows over time, then the most probable state of the universe is maximum chaos, a featureless soup of particles. The fact that we see structure, galaxies, planets, our own bodies suggests we're in a statistically unlikely low entropy pocket, Boltzmann's original solution. Maybe we're just a rare fluctuation in an otherwise dead cosmos, but take that logic further. If random fluctuations can create entire solar systems, why not skip the middleman and just create lone, self-aware minds drifting in the dark? Physicists recoil from this idea for good reason. A universe teeming with Boltzmann brains undermines the foundation of scientific reasoning. If most observers are illusions, how can we trust any of our perceptions? The laws of physics, the fossil record, even your childhood memories could be elaborate hallucinations generated by a disembodied brain that formed 5 seconds ago. It's the ultimate solipsistic nightmare, and yet, in an infinite universe governed by probability, it's technically possible. Most researchers dismiss Boltzmann brains as absurd, not because they can disprove them, but because accepting them would render science meaningless. Instead, they look for loopholes. Maybe the universe isn't infinite. Maybe dark energy will rip space-time apart before Boltzmann brains have time to form. Or maybe, just maybe, the fact that we don't observe them is a clue that reality isn't as random as it seems. But until we crack the deepest mysteries of entropy and cosmology, the Boltzmann brain lingers like a ghost in the equations, a reminder that the universe might be stranger and far lonelier than we ever dared to fear. What if the universe isn't a vast, indifferent expanse but an elaborate simulation running on some advanced civilization's supercomputer? This is the simulation hypothesis, a theory that's equal parts philosophy and futurism, and it hinges on a startling trilemma posed by philosopher Nick Bostrom. He argued that at least one of these 3 statements must be true. 1. Virtually all civilizations at our level of technological development go extinct before becoming capable of creating realistic simulations. 2. If any civilizations do reach that stage, they almost never choose to run ancestor simulations, digital recreations of their past. Or 3. We're almost certainly living in one of those simulations right now. Bostrom's logic is deceptively simple. If future civilizations develop the computing power to simulate conscious minds, and if they have any interest in recreating their history, then the number of simulated beings would dwarf the number of biological ones. Think about it. One advanced society could run billions of simulations, each containing billions of digital humans. The odds that we're among the original, real minds shrink to virtually zero. It's like walking into a room filled with identical paintings and assuming you're looking at the one true Mona Lisa while the rest are copies. The sheer math makes it overwhelmingly likely we're in the replica. But how close are we to building such simulations? The technological hurdles are staggering. Creating a universe-sized simulation atom by atom would require energy and processing power beyond anything we can fathom. But here's the twist: a convincing simulation doesn't need to render every quark in real time. Just like a video game only loads the parts of the world you're looking at, a hyper-intelligent civilization might only simulate the parts of reality being observed, a trick called quantum rendering. This idea got a boost when physicists discovered our universe behaves suspiciously like optimized code. Quantum particles only settle into definite states when measured, as if processing power is being conserved. Some researchers take this further, actively hunting for glitches in the matrix. If our reality is a simulation, it might have shortcuts or errors, tiny cracks in the facade. Scientists have proposed experiments to detect pixelation in spacetime at the Planck scale, or anomalies in the cosmic microwave background that resemble the artifacts in a compressed image. Others point to déjà vu, quantum indeterminacy, or even dreams as potential bugs in the system. Then there's Elon Musk, who famously declared the odds we're not in a simulation are 1 in billions, arguing that 40 years of gaming progress, from Pong to photorealistic VR, suggests we're just decades away from creating indistinguishable digital worlds ourselves. But the simulation hypothesis isn't without critics. Some call it unfalsifiable, a clever thought experiment with no way to prove or disprove it. Others argue it's a high-tech repackaging of age-old solipsism, the fear that nothing outside our minds is real. And then there's the existential kicker. If we're simulations, are our creators simulations too? An infinite regress of nested realities, each unaware of the one above it. Whether the theory holds water or not, it forces us to confront a profound question. Does it matter if reality is base level or not? The stars still shine, love still hurts, and curiosity still drives us, simulated or not. The universe feels real enough to explore. Imagine if scientists could detect the pixels of reality itself, tiny, indivisible chunks of spacetime that might betray our universe's digital origins. The idea isn't as far-fetched as it sounds. Physicists have proposed real experiments to hunt for these cosmic glitches. One approach involves ultra-precise measurements of high-energy gamma rays from distant quasars. If spacetime is pixelated at the Planck scale, the smallest possible unit of measurement, then these rays, traveling billions of light-years, might arrive slightly out of sync, as if they'd hit invisible speed bumps in the fabric of reality. It's like watching a streaming video with low bandwidth. The data gets choppy, revealing the underlying code. Experiments like the Fermi Gamma Ray Space Telescope are already scanning for these anomalies, searching for whispers of a simulated universe in the static of the cosmos. Another frontier is quantum gravity research. If the universe is a computation, there must be fundamental limits to how much information can be processed in a given volume. A cosmic version of your laptop overheating if you run too many programs at once. Theorists like Silke Weinfurtner have designed lab experiments using superfluid helium to mimic spacetime's behavior, watching for telltale signs of pixelation or frame rate drops in the quantum foam. Meanwhile, the holometer at Fermilab attempted to detect spacetime's quantum jitter by firing lasers down perpendicular tunnels, looking for interference patterns that might reveal the universe's resolution limit. So far, the results have been inconclusive, but the hunt continues, fueled by the tantalizing possibility that we might one day bump against the edges of the simulation. But what if we do find evidence the universe is coded? Philosophers split into warring camps. Some argue the discovery wouldn't change much after all. The laws of physics would still govern our experience, making the simulation functionally indistinguishable from base reality. Others counter that it would upend everything from ethics to identity. If we're artificial constructs, do our choices matter? Do our creators bear moral responsibility for our suffering? And what happens if they shut the simulation down? The debates echo age-old theological questions about predestination and free will, now dressed in silicon instead of scripture. At the heart of this is the so-called problem of other minds. If we're simulations, are the people around us truly conscious or just convincing NPCs, non-player characters running on autopilot? Some thinkers propose a chilling middle ground. Simulated consciousness might be real consciousness, just running on a different substrate. After all, if thoughts are just information processing, does it matter whether the processor is made of neurons or qubits? The line between real and simulated blurs until it vanishes entirely, leaving us with a paradox. The more we probe the nature of reality, the less solid any definition of real becomes. Ultimately, the simulation hypothesis forces us to confront not just the universe's mysteries, but the limits of human cognition itself. Whether we're strings of code or stardust, the questions we ask and the experiments we devise reveal something profound. The universe, simulated or not, is stranger than our tools can yet measure, and more wondrous than our theories can yet explain. What if time isn't a river flowing from past to future, but a frozen landscape where every moment exists simultaneously, and our brains are just stitching them together into an illusion of motion? Physicist Julian Barber's radical theory of timeless physics suggests exactly that. Time isn't fundamental to the universe at all. Instead, reality might be a vast, static tapestry of nows called Platonia, where change is real but time is merely a trick of perception. Picture a cosmic flipbook where every page exists at once, and consciousness is the thumb giving the illusion of animation. This idea isn't pure philosophy. It's grounded in the Wheeler-DeWitt equation, a cornerstone of quantum gravity research. When physicists Bryce DeWitt and John Wheeler tried to merge Einstein's general relativity with quantum mechanics, they stumbled on something bizarre. Time vanished from the math entirely. The equation describes the universe as a timeless whole with no variable marking before or after. It's as if the universe is a single, unchanging quantum state, and what we experience as time is just our limited way of navigating it. Think of it like watching a single frame of a movie and insisting it's moving when in reality, the entire film is already printed on the reel. But how does this square with our undeniable experience of time's flow? Neuroscience offers a clue. Our brains construct temporal sequences by stitching together sensory inputs, memories, and anticipations, creating the sensation of a continuous narrative. Experiments show that our perception of now is actually a delayed reconstruction, like a live broadcast with a half-second delay. When you touch a hot stove, the pain seems instantaneous, but your brain backdates the sensation to match the visual input. This mental timekeeping might be the only time that truly exists, a fragile consensus forged by neurons firing in the dark. Critics argue timeless physics can't explain causality. How causes precede effects if time isn't real? Barber counters that causation emerges from relationships between configurations, not from temporal order. Imagine dominoes falling in a frozen mosaic. Their arrangement implies a sequence, even if no domino actually moves. Similarly, the universe's structure might encode what we call time purely through patterns of connection. Quantum gravity approaches like loop quantum gravity and string theory tentatively support this, suggesting spacetime could be granular, built from discrete quantum bits that only appear continuous from our macroscopic vantage. The implications are dizzying. If time is illusory, free will takes on new dimensions, not as choices made in a flowing stream, but as configurations already etched into the cosmic mosaic. Death, too, transforms not an end, but one now among infinite others, forever preserved in Platonia's gallery. Even entropy, the arrow of time's backbone, might be a side effect of how we slice reality. As Barber puts it, the past is just memories, the future is imagination. All we ever have is this. So the next time you check your watch, ask yourself, are you measuring time or just the mind's desperate attempt to make sense of eternity? If black holes are the universe's ultimate trash compactors sucking in matter and never letting go, then white holes are their cosmic opposites, spewing out energy and matter like an unstoppable fountain. Now take that idea and stretch it to the beginning of everything. What if the Big Bang wasn't a singularity, but a white hole's grand finale? This is the spine of white hole cosmology, a theory that flips our understanding of the universe's birth on its head. While black holes trap everything behind an event horizon, white holes theoretically have an anti-horizon, a boundary that only ejects. Picture a cosmic fire hose blasting spacetime itself into existence, and you're starting to grasp the sheer audacity of this idea. Roger Penrose, the Nobel-winning physicist who helped pioneer black hole theory, took this even further with his conformal cyclic cosmology. He proposed that our universe's death in the far future, a cold, empty expanse where black holes have evaporated, might mathematically resemble the conditions of the Big Bang. In this mind-bending framework, the end of one universe becomes the white hole birth of another, cycling eternally through what Penrose calls eons. The equations suggest something eerie. The infinite future of one epoch could seamlessly connect to the infinite past of the next, like a Möbius strip of cosmic time. Critics argue this stretches general relativity to its breaking point, but Penrose points to faint circular patterns in the cosmic microwave background, potential Hawking points, left by ancient black holes from a previous eon. Now, how would we even test such a wild idea? White holes, if they exist, should leave distinct fingerprints. Unlike black holes, which pull in surrounding gas and dust, a white hole would repel matter, creating a characteristic void in space. Some astronomers have scoured galaxy surveys for these odd empty regions, while others hunt for unexplained gamma-ray bursts that match the theoretical energy profile of a white hole's eruption. Then there's the quantum angle. Certain interpretations of loop quantum gravity suggest that when a black hole's collapse reaches maximum density, quantum effects could cause a bounce, transforming it into a white hole. If true, microscopic white holes might be hiding in the cosmos today, relics of tiny black holes born in the early universe. The implications ripple through philosophy as much as physics. If white hole cosmology holds, our universe isn't a one-time event but a link in an endless chain, where every ending seeds a new beginning. Time loses its arrow, becoming a wheel where entropy resets with each cycle. It's a vision both humbling and exhilarating, one where the cosmos isn't just expanding but breathing, and whether Penrose's circles in the sky are echoes of a past universe or cosmic static, one thing's certain: the universe's origin story might be far stranger than we ever dreamed. What if consciousness isn't something the universe has, but something it is? Panpsychism, the idea that mind is a fundamental feature of reality, flips the traditional view of consciousness on its head. Instead of treating it as an accidental byproduct of brain chemistry, this theory suggests even the smallest particles might possess some rudimentary form of experience. Not in the way humans think or feel, but as a basic property woven into the fabric of spacetime itself, like mass or charge. At first glance, it sounds like mysticism, but serious physicists and philosophers are exploring how this radical perspective might solve the hard problem of consciousness, the puzzle of why and how subjective experience emerges from mere matter. Integrated information theory, or IIT, offers a mathematical framework for this idea. Developed by neuroscientist Giulio Tononi, IIT proposes that consciousness isn't binary, on or off, but exists on a spectrum. Any system with the right internal structure, from a human brain to a thermostat, could possess some degree of experience. The key is phi, a measure of how interconnected and causally rich a system's components are. The higher the phi, the more unified and complex the conscious experience. Under this model, even inanimate objects might have whisper-thin glimmers of awareness, while human brains hum with the symphony of selfhood. Critics argue this risks over-attributing consciousness, but supporters counter that it elegantly bridges the gap between physics and phenomenology, the study of lived experience. Quantum mechanics adds another layer to the puzzle. Some researchers, like Nobel laureate Roger Penrose and anesthesiologist Stuart Hameroff, propose that consciousness arises from quantum processes inside neurons, specifically tiny structures called microtubules. Their arch or theory suggests these microtubules perform quantum computations, collapsing wave functions in a way that generates subjective awareness. If true, it implies the universe's quantum underpinnings might be inherently conscious, with our minds as localized amplifications of that deeper sentience. Skeptics dismiss this as speculation, pointing out the brain's warm, noisy environment would likely disrupt delicate quantum states. Yet experiments keep hinting at quantum effects in biology, from photosynthesis to bird migration, leaving the door cracked for mind-blowing possibilities. The implications ripple far beyond neuroscience. If panpsychism holds, the cosmos might be more like a vast, dreaming entity than a cold, empty machine. Black holes could process information in ways we'd recognize as thought. Galaxies might possess a slow, glacial form of self-reflection. Even the vacuum of space could thrum with proto-consciousness, a cosmic murmur beneath the silence. This isn't about attributing human-like thoughts to stars, but recognizing that subjectivity might be as universal as gravity, a thread running through reality at every scale. So where does this leave the hard problem? Panpsychism doesn't so much solve it as dissolve it, suggesting consciousness was never an emergent property to begin with, but a foundational one. The universe didn't create minds, it is mind in endless variations. Whether you find this idea exhilarating or unsettling, one thing's clear. If true, we're not just observers of the cosmos, we're the universe itself, waking up piece by piece to wonder at its own existence. What if our universe isn't just expanding, but being dragged? Astronomers have stumbled upon a phenomenon so bizarre, it's been dubbed dark flow, a mysterious, coordinated motion of galaxy clusters hurtling in the same direction at breakneck speeds, as if pulled by some unseen force beyond the edge of everything we know. Imagine throwing a handful of paper airplanes into the wind, only to watch them all curve toward a hidden storm just over the horizon. That's the unsettling puzzle dark flow presents. Something out there, beyond our cosmic vision, is yanking entire clusters of galaxies like puppets on strings. The first clues emerged from NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, which mapped the faint afterglow of the Big Bang, the cosmic microwave background. Scientists expected this radiation to be nearly uniform, but the data revealed strange, elongated temperature shifts aligned with the direction of the dark flow, as if space-time itself were being stretched by an immense gravitational tug. Later, the Planck satellite confirmed these anomalies, ruling out measurement errors. The numbers were clear: hundreds of galaxy clusters, some over 3 billion light-years apart, were all streaming toward the same patch of nothingness at speeds exceeding 2 million miles per hour. So what could possibly exert that kind of pull? One spine-tingling possibility is that our universe is just one bubble in an infinite multiverse, and these clusters are feeling the gravity of another cosmos brushing against ours. Picture two soap bubbles floating in a sink, where they nearly touch, the surface tension warps, creating a subtle pull. If another universe existed beyond our observable horizon, its mass, completely invisible to us, could be bending the fabric of shared space-time, dragging everything toward it. Another theory points to primordial defects in the structure of reality, like cosmic strings, hypothetical, ultra-dense threads left over from the Big Bang acting as gravitational lassos. Yet dark flow remains controversial. Some researchers argue it's a statistical fluke or an artifact of how we measure large-scale motion. Others propose less exotic explanations, like incomplete maps of local matter distribution creating the illusion of a pull. But if the effect is real, the implications rewrite cosmology. It would mean the observable universe isn't just a tiny fraction of reality. It's a fishbowl floating in an ocean of something else, a realm where the rules of physics might be unrecognizable. The most haunting question isn't just what's pulling us, but how far it lies. If the source is beyond the cosmic horizon, the point where expansion pushes light away faster than it can reach us, we may never see it directly. Like shadows on a cave wall, we'd only ever glimpse its influence, left to wonder what unimaginable structures lurk in the dark. Whether it's a neighboring universe or a flaw in our theories, dark flow whispers one thing: we're not at the center of anything. The cosmos is vaster, stranger, and far more restless than we ever dreamed. What if the Big Bang wasn't the beginning of everything, just the latest chapter in an endless cycle of cosmic rebirth? The Big Bounce theory reimagines the universe's story not as a single explosive origin, but as an infinite loop of expansion and contraction, where each collapse becomes the seed for the next explosion. Picture a cosmic lung inhaling spacetime into a dense crunch, then exhaling it back out in a fiery rebirth. This isn't just poetic imagery, it's a serious alternative to the traditional Big Bang model, one that sidesteps the need for a singularity, a point of infinite density where physics breaks down entirely. Loop quantum gravity, a leading candidate for unifying quantum mechanics and general relativity, provides the math to make this possible. Unlike classical physics, which predicts matter gets crushed into oblivion during a collapse, loop quantum gravity suggests spacetime is granular at the smallest scales, woven from tiny, indivisible loops. When the universe contracts to a certain threshold, these loops resist further squeezing, creating a repulsive force powerful enough to reverse the collapse into a bounce. Think of it like compressing a spring, push hard enough and it snaps back. In this model, the Big Bang wasn't a beginning from nothing, it was the universe hitting its limit and rebounding, like a phoenix rising from its own ashes. But there's a catch: entropy. The second law of thermodynamics states that disorder in a closed system always increases, and critics argue this poses a fatal flaw for cyclical models. If each cycle inherits the entropy of the last, the universe should grow more chaotic over time, like a photocopy of a photocopy degrading with each iteration. After countless bounces, we'd expect a heat-soaked, lifeless cosmos, not the structured, low-entropy universe we see today. Some theorists counter that entropy might somehow reset during the bounce, perhaps through quantum effects or exotic new physics. Others propose that dark energies accelerating expansion could stretch spacetime so thin that entropy effectively dilutes between cycles, like hitting a cosmic reset button. The Big Bounce also raises profound questions about time's arrow. If the universe reverses its collapse, does time run backward in the contracting phase? Not necessarily. Physicists like Sean Carroll suggest entropy could continue increasing even during the crunch, meaning time's flow would feel consistent from one cycle to the next. You wouldn't suddenly see shattered cups reassemble, just a universe growing denser and hotter until the bounce flips the script again. Skeptics aren't convinced. Without observational evidence, the Big Bounce remains speculative, and competing models like eternal inflation or Penrose's conformal cyclic cosmology offer different takes on cosmic recycling. Yet the theory's appeal is undeniable. It trades a single, inexplicable beginning for an eternal rhythm, where endings birth new beginnings. Whether the math ultimately holds or not, the Big Bounce challenges us to rethink the universe's deepest cadence not as a one-time symphony, but as an infinite refrain playing across the eons. What if the entire universe, every galaxy, every atom, every second of history, is unfolding inside the belly of a black hole? This isn't just science fiction, it's a legitimate hypothesis that reshapes our understanding of reality. Think about the eerie parallels. At the heart of a black hole lies a singularity, a point of infinite density where space and time break down. Now rewind our cosmic clock to the Big Bang, and what do we find? Another singularity, another moment where the rules of physics seem to vanish. Could these two extremes, one pulling matter in, the other spewing it out, be two sides of the same cosmic coin? The math gets even stranger when you consider the holographic principle. Black holes don't destroy information, they encode it on their event horizons like cosmic hard drives. Now zoom out to our universe. If the holographic principle holds, all the information in our three-dimensional reality might be stored on a two-dimensional boundary at the edge of space. Sound familiar? It's as if our universe is running on the same operating system as a black hole, a massive, self-contained simulation where the laws of physics are just lines of code written on the walls of our cosmic prison. Physicist Lee Smolin took this idea even further with his theory of cosmological natural selection. He proposed that black holes could be cosmic wombs birthing new universes inside them, each with slightly tweaked physical constants. Universes that produce more black holes would, in turn, spawn more offspring, creating an evolutionary pressure favoring fertile universes like ours. It's a dizzying thought. The reason our universe seems fine-tuned for life might not be divine intervention, but simple Darwinism playing out across unimaginable scales. After all, if gravity were slightly weaker, stars wouldn't collapse into black holes, meaning no baby universes, no cosmic lineage. Critics argue this theory is untestable, a metaphysical shrug disguised as physics. But supporters point to subtle clues. For instance, if we're inside a black hole, the universe's expansion could be the slow-motion echo of that initial implosion, like a rubber band stretching after being snapped. And the cosmic microwave background, the afterglow of the Big Bang, might bear faint imprints of the parent black hole's structure, hidden in patterns we've yet to decode. The implications are staggering. If true, every black hole in our universe could contain an entire cosmos, each with its own black holes, each nesting realities like infinite Russian dolls. Suddenly, the phrase, "as above, so below," takes on new meaning not as mysticism but as physics. Whether this theory holds or not, one thing's certain: the universe has a flair for turning science into poetry, where even the darkest voids might cradle entire worlds. What if the universe's fate isn't just to fade into cold darkness, but to be violently shredded apart, atom by atom, in a cataclysm so absolute it makes black holes look gentle? This is the nightmare scenario known as the Big Rip, a hypothesis where dark energy, the mysterious force accelerating cosmic expansion, doesn't just push galaxies apart but grows infinitely stronger, eventually overwhelming every force that holds reality together. Picture spacetime itself as a piece of fabric stretched thinner and thinner until it can't take the tension anymore. First, galaxies are torn from each other, then stars from their orbits, then planets from their suns, until finally, even atoms are ripped into quarks, dissolving the very building blocks of existence into a formless void. The math behind this apocalyptic vision hinges on dark energy's equation of state, represented by the letter W. In simple terms, this number describes how dark energy's density changes as the universe expands. If W equals -1, dark energy remains constant, leading to the more familiar heat-death scenario where expansion continues steadily but doesn't intensify. But if W is less than -1, say, -1.5, dark energy's grip tightens over time, its density growing as space stretches. It's like a car's accelerator pedal getting stuck to the floor. Expansion starts slow, then spirals out of control until spacetime itself becomes the casualty. Observational data paints a mixed picture. Measurements of supernova, galaxy clusters, and the cosmic microwave background currently peg W close to -1, with a slight margin of error that keeps the Big Rip on the table. Some astronomers argue that certain quirks in the distribution of distant galaxies hint at dark energy's strengthening influence, while others dismiss these as statistical noise. The problem is, dark energy's effects are subtle on human timescales, like trying to sense the curvature of Earth while standing in a parking lot. We're left peering into the cosmic fog, searching for clues in the dim light of exploding stars and the ghostly echoes of the Big Bang. Yet, even if the Big Rip remains speculative, its implications haunt physics. If dark energy can grow strong enough to tear apart atoms, what does that say about the fundamental forces we thought were unshakable? Electromagnetism and the strong nuclear force have held the universe together for billions of years. But in the face of runaway expansion, they might be as fragile as tissue paper. Some theorists propose that a phantom energy field with W values plunging far below -1 could trigger this rupture, its energy density skyrocketing so fast that it defies conventional physics. Others suggest the Big Rip wouldn't just destroy matter. It might rewrite the laws of physics on its way out, leaving behind a barren wasteland where not even time has meaning. The eerie beauty of this theory is its inevitability. If the Big Rip is real, no technology, no cosmic escape plan could save us. The rupture would happen everywhere at once, a silent, instantaneous end with no warning. Yet there's a strange comfort in its impartiality. No civilizations, no gods, no black holes would be spared. The universe would meet its end not with a whimper, but with a scream, a final, fleeting moment where every particle, from the densest star to the air in your lungs, realizes it's alone. And then nothing, not even memories, just the phantom imprint of a cosmos that once was, stretching into oblivion. What if the Big Bang wasn't a fiery explosion, but the cosmic equivalent of a car crash? The ekpyrotic universe theory throws out the traditional image of a singularity bursting into existence, replacing it with something even stranger. Our universe as a three-dimensional brain, floating in a higher dimensional space, colliding with another brain like two sheets of paper slamming together. This collision wouldn't just be violent, it would release enough energy to mimic the heat and density of the Big Bang, jump-starting everything we know without requiring a singularity's infinite density. And here's the twist: this process might not be a one-time event, but part of an endless cycle where brains attract, collide, rebound, and repeat, birthing universes in an eternal cosmic tango. The idea springs from string theory, which proposes that the fundamental particles of nature aren't dots but tiny, vibrating strings. To make the math work, these strings need more room than our familiar 3 dimensions. Some versions of the theory require 10 or even 11 dimensions. In this higher dimensional bulk, our universe could be just one membrane or brain among many, each existing like a slice of bread in a multidimensional loaf. The ekpyrotic model, from the Greek word for conflagration, suggests that when two such brains collide, the kinetic energy transforms into the hot, dense soup of particles we call the Big Bang. It's like clapping your hands. The moment of impact creates heat, sound, and motion, but your hands remain intact. Unlike cosmic inflation, which imagines space stretching exponentially in a fraction of a second, the ekpyrotic scenario solves several cosmological puzzles with its cyclical nature. For starters, it avoids the need for a singularity, that pesky point of infinite density where physics breaks down. Instead, the brains approach each other smoothly, collide, and separate again, with each cycle resetting the cosmic clock. This also addresses the universe's eerie flatness and uniformity, the fact that the cosmos looks roughly the same in all directions. Inflation explains this by proposing a rapid smoothing process, but the ekpyrotic model achieves the same result through the brain's gentle pre-collision stretching, which flattens and homogenizes them like dough rolled thin before baking. Critics raise tough questions, though. If brains collide to create universes, what set them in motion to begin with? Some versions of the theory invoke dark energy or scalar fields to drive the cycles, but these ideas remain speculative. There's also the problem of entropy. Like the Big Bounce, cyclic models must explain how each reset doesn't trap the universe in a heat-death spiral. Proponents argue that the collision and separation phases could reorganize entropy, like shuffling a deck of cards back into order, though skeptics call this hand-waving. The most tantalizing difference between ekpyrosis and inflation lies in their fingerprints. Inflation predicts a specific pattern of gravitational waves imprinted on the cosmic microwave background, while ekpyrosis suggests a fainter, more nuanced signal. So far, experiments haven't found conclusive evidence for either, leaving the debate wide open, but the stakes couldn't be higher. If the ekpyrotic model is right, our universe isn't a lonely one-off, it's one note in an endless symphony of collisions, each crash echoing with the birth of a new cosmos. And somewhere out there in the bulk, another brain might be drifting toward us, carrying the spark of the next Big Bang. What if the very fabric of time isn't just a passive backdrop, but a dynamic structure with its own rhythm, one that never winds down, never loses energy, ticking forever like a cosmic metronome? That's the revolutionary idea behind time crystals, a bizarre phase of matter first proposed by Nobel laureate Frank Wilczek. Unlike ordinary crystals, which repeat their atomic patterns in space, think of the symmetrical lattice of a diamond. Time crystals repeat their patterns in time, oscillating between states without any energy input. It's as if you could build a clock that ticks forever without batteries, powered not by external forces but by the universe's own rule-breaking physics. Wilczek's theory hinges on something called discrete time translation symmetry breaking. Normally, the laws of physics look the same no matter when you observe them, a principle known as time translation symmetry. But time crystals shatter this expectation. Imagine a toy car that moves forward every 2 seconds, then pauses, then repeats. The system doesn't respect the symmetry of each individual second. Instead, it chooses to oscillate on its own schedule, creating a pattern locked in time. In a lab, this might manifest as a ring of ions flipping their quantum spins in a persistent rhythm, not because they're being nudged by lasers, but because the system's lowest energy state, its quantum ground state, naturally settles into this eternal dance. The implications are mind-bending. Time crystals aren't just a laboratory curiosity, they challenge our understanding of thermodynamics itself. Perpetual motion has always been dismissed as impossible, a violation of energy conservation. Yet time crystals achieve motion without energy loss, not by breaking the rules but by exploiting quantum loopholes. They don't create energy, they redistribute it in a way that locks oscillations into the fabric of reality. Experiments at Stanford and Harvard have brought these theories to life, using diamond defects and superconducting qubits to create the first time crystalline structures. The results, systems that pulse like tiny atomic hearts, indifferent to the universe's slow march toward entropy. Could time crystals be more than just lab-made oddities? Some theorists speculate they might exist naturally in extreme cosmic environments, maybe inside neutron stars, where gravity warps spacetime into knots, or threading through the quantum vacuum itself. If true, the universe might be humming with hidden rhythms, a symphony of perpetual motion written into the fine print of physics. For now, time crystals remain a tantalizing glimpse into a deeper layer of reality, where time isn't just a dimension we move through, but a structure that moves itself forever. What if everything around us, the stars, the planets, even your own body, is just a fleeting ripple in an infinite void, a momentary spark in an otherwise empty cosmic furnace? That's the radical premise of the quantum fluctuation theory, which suggests our universe might owe its existence to a random flicker in the quantum vacuum. Picture the fabric of reality as a bubbling pot of water, where tiny pockets of energy pop in and out of existence so quickly they're nearly imperceptible. Now imagine one of those bubbles didn't vanish but grew, inflating into the sprawling cosmos we call home. At the heart of this idea is Edward Tryon's groundbreaking proposal from 1973 that our universe could be a zero-energy fluctuation. Here's the mind-bending part. The universe appears to contain an enormous amount of mass and energy, stars, galaxies, dark matter, but gravity's pull introduces a negative energy component. Add them together and the total might actually sum to zero. It's like taking out a loan to buy a house. The house has positive value, the debt has negative value, and the net worth remains balanced. In cosmic terms, the universe might be the ultimate free lunch, borrowing energy from the quantum vacuum and paying it back with gravitational interest over billions of years. Quantum mechanics lends eerie support to this notion. Empty space, far from being truly empty, seethes with virtual particles that blink into existence for fractions of a second before annihilating each other. These quantum fluctuations are well documented. They're responsible for effects like Hawking radiation and the Lamb shift in atomic spectra. But what if, in the extreme conditions of the early cosmos, one of these fluctuations didn't cancel out? What if it got stretched by inflationary expansion, freezing into permanence like a wave caught mid-crash? Critics argue that even if the math balances, the odds of a fluctuation birthing an entire universe are infinitesimal. Yet in an infinite or eternal multiverse, even the most improbable events become inevitable. Think of it like shuffling a deck of cards forever. Eventually, you'll deal out a perfect bridge hand. The quantum fluctuation theory turns cosmic genesis from a singular miracle into a statistical inevitability, where universes pop into being like bubbles in a froth of nothingness. The implications are staggering. If true, our universe isn't special or destined just one random roll of the quantum dice. It also raises spine-tingling questions about what lies beyond our cosmic horizon. Are other fluctuations blooming into universes even now, each with its own laws of physics? And if our universe is a temporary bubble, could it one day collapse back into the void, vanishing as suddenly as it appeared? For now, these questions linger at the edge of science, where physics and philosophy blur into wonder. One thing's certain: whether a divine act or a quantum hiccup, existence remains the most mesmerizing mystery of all. What if every electron in the universe, from the ones powering your screen right now to those dancing in distant galaxies, was actually the same particle zigzagging frenetically through time? This is the audacious heart of John Wheeler's one-electron universe hypothesis, a theory so radical it blurs the line between profound insight and cosmic poetry. Picture a single electron not as a tiny dot but as an endless thread stitching through spacetime, looping backward and forward so deftly that it appears to be everywhere at once. When it moves forward in time, we see an electron. When it reverses, we call it a positron, the electron's antimatter twin. In this mind-bending view, the countless electrons we observe could just be one entity tangled in a labyrinth of its own making. Wheeler's inspiration came from a conversation with Richard Feynman, who'd proposed that positrons might simply be electrons traveling backward in time. The math checked out. Antimatter particles do behave like normal matter, moving in reverse, flipping charge and energy as if rewinding a film. Wheeler took this further, speculating that if one electron could hopscotch through time, why not all of them? The universe's entire electron population might be a single particle's itinerary, its world line crisscrossing eternity like a ball of yarn tossed into the fourth dimension. But why stop at electrons? The theory stumbles when applied to other particles. Muons, quarks, and neutrinos don't neatly mirror their antimatter counterparts in the same way. Positrons and electrons are unique in their symmetry, a perfect duality that collapses when extended to heavier, more complex particles. There's also the elephant in the room. If all electrons are one, why do we see so many simultaneously? Wheeler imagined the electron's path might be so convoluted, weaving through every moment of cosmic history, that it appears omnipresent. Think of a dancer spinning so fast their arms seem to be in multiple places at once, a trick of perspective scaled to universal proportions. The implications flirt with philosophical vertigo. If true, the one-electron universe would mean every interaction, every chemical bond, every spark of electricity is just the same timeless actor playing infinite roles. Your body, your devices, the stars, all just stages for this solitary particle's endless performance. Critics argue this is less a testable theory than a beautiful metaphor, a reminder of how deeply interconnected reality might be at its core. Yet, even as a thought experiment, it challenges our assumptions about identity and permanence, whispering that the universe's building blocks might be far stranger than they appear. Perhaps the most haunting question isn't whether Wheeler was right, but what his idea reveals about our place in the cosmos. In a universe where a single electron could be everywhere and everyone, the line between one and many, between particle and pattern, dissolves into pure wonder. Picture the universe not as a vast, empty expanse dotted with galaxies, but as a living organism, its structure mirroring the intricate patterns of cells under a microscope. This is the essence of the cellular universe theory, a fractal vision where clusters of galaxies resemble the branching networks of neurons or the delicate lattice of veins in a leaf. Zoom far enough into a neuron, and its structure echoes the cosmic web of dark matter and galaxies. Zoom out from a galaxy cluster, and suddenly, it looks uncannily like a single cell in some unimaginably large body. The idea isn't just poetic, it's rooted in the mathematical principle of self-similarity, where patterns repeat at every scale from quarks to quasars. At the heart of this theory lies fractal cosmology, championed by physicists like Laurent Nautile. It suggests that the distribution of matter in the universe isn't random but follows a repeating, nested pattern like Russian dolls of cosmic structure. Proponents point to galaxy surveys revealing clusters within clusters, filaments within filaments, all arranged in ways that defy expectations of uniformity. Even the cosmic microwave background, the afterglow of the Big Bang, shows fluctuations that some argue resemble fractal geometry. If true, this would imply the universe isn't just expanding but organizing itself according to deep, hidden symmetries, as if obeying some primordial blueprint. Yet the cellular universe model faces fierce opposition, particularly from advocates of plasma cosmology like Eric Lerner. He argues that the Big Bang's dominance has overshadowed alternative explanations for cosmic structure, especially those involving electromagnetic forces. In Lerner's view, galaxies and clusters aren't sculpted by dark matter's gravity alone, but by vast currents of ionized plasma, charged particles threading through space like cosmic bloodstreams. These currents, he claims, could generate the filamentary structures we see without invoking invisible matter or an initial singularity. Plasma cosmology draws inspiration from laboratory experiments where electrified gases spontaneously form spiral and filament patterns eerily reminiscent of galaxy shapes. The debate hinges on observations. Big Bang cosmology predicts a specific distribution of matter, one that aligns with computer simulations of dark matter's gravitational pull. But critics like Lerner highlight anomalies, galaxies rotating too fast for their visible mass, clusters appearing older than the universe itself, and large-scale structures so vast they shouldn't have had time to form. To plasma cosmologists, these aren't puzzles to be solved by inventing new particles but evidence that we've misunderstood cosmic dynamics. They point to the success of plasma physics in explaining solar flares and auroras, arguing the same principles might govern the cosmos at large. The cellular universe theory, whether fractal or plasma-driven, ultimately challenges us to rethink scale and connection. Are we the microscopic inhabitants of some greater cosmic body, or is the universe less a machine and more an organism, growing and evolving in ways we've barely begun to decipher? The answer might lie in the patterns we've yet to notice hidden in the glow of distant quasars or the magnetic whispers of interstellar plasma. Until then, the universe remains both a puzzle and a mirror, reflecting back the shapes of life in its grandest designs. What if the universe isn't just a machine of cold, indifferent forces, but a living, evolving entity, constantly reorganizing itself like a vast cosmic organism? The living universe theory takes inspiration from Earth's biosphere, where life emerges from intricate feedback loops, and asks, could the cosmos itself operate on similar principles? This isn't just poetic musing, it's a serious scientific framework that challenges our deepest assumptions about space, time, and the nature of existence. At its core is the radical notion that complexity isn't accidental, it's the universe's way of growing, learning, and perhaps even reproducing. Lee Smollen's fecund universes hypothesis offers one provocative angle. Imagine black holes not as dead ends but as cosmic wombs. Every time a star collapses into a singularity, the extreme conditions might spawn a new universe inside it, one with slightly tweaked physical constants. Universes that produce more black holes would, in turn, generate more offspring, creating a kind of Darwinian selection pressure on cosmic scales. Over countless generations, universes fine-tuned for black hole production, and thus for complexity, would dominate the multiverse landscape. It's a breathtaking vision, the cosmos as a sprawling family tree, with our universe just one branch among many, shaped by the same evolutionary forces that sculpt life on Earth. But self-organization goes beyond black holes. Think of the cosmic web, the vast, filamentary structure of galaxies stretching across the void. These threads aren't random. They're the result of gravity amplifying tiny quantum fluctuations from the Big Bang, sculpting order from chaos over billions of years. This process mirrors how living systems grow, from the branching veins in a leaf to the neural networks in your brain. Some theorists argue this isn't just analogy but evidence of deeper principles at work. Complexity might be an inevitable feature of any universe with the right ingredients: energy gradients, feedback loops, and time, lots of time. Thermodynamics adds another layer to the mystery. Life on Earth thrives by exporting entropy, maintaining internal order at the expense of its surroundings. Could the universe do something similar? The late physicist Freeman Dyson speculated that advanced civilizations might one day harness entropy itself, using it as a resource to sustain complexity indefinitely. In this view, the cosmos isn't doomed to a heat death but might instead find ways to recycle its energy, much like ecosystems recycle nutrients. Even dark energy, the mysterious force accelerating cosmic expansion, could play a role. Some models suggest it might fuel future phases of self-organization, triggering new cycles of structure formation long after stars have burned out. Critics dismiss these ideas as speculative, even mystical. Yet the parallels are hard to ignore. From galaxies to cells, nature seems obsessed with repeating patterns, as if hinting at a unified logic governing all scales. Whether you call it Gaia cosmology, panpsychism, or simply a new kind of physics, the living universe theory invites us to see reality not as a static backdrop but as an active participant, a great breathing thing that's still discovering what it can become. And if that's true, then every atom, every star, every conscious mind might be part of something far grander, a cosmos not merely existing but alive. What if the universe isn't just governed by physics but is, at its core, an unfathomably vast thinking machine? This radical idea that reality itself might emerge from some form of cosmic computation has moved from science fiction to a legitimate frontier of theoretical physics. At the heart of this concept lies a startling parallel. The structure of spacetime might not be so different from the architecture of artificial neural networks, those webs of interconnected nodes that power everything from facial recognition to weather forecasting. The foundation for this theory comes from tensor networks, mathematical frameworks originally developed to simplify complex quantum systems. Imagine spacetime as an intricate mesh of information where each intersection point, each node, holds a fragment of data about the state of the universe. These nodes communicate with their neighbors, passing and processing information in a way eerily similar to how neurons fire in a brain. Physicists like Brian Swingle and Xiao Liang Kai have shown that these networks can reproduce key features of general relativity, suggesting space itself might emerge from these underlying computational exchanges. It's as if Einstein's curved spacetime isn't the deepest layer of reality, but the user interface a smooth projection built atop countless discrete calculations. Now consider recent advances in machine learning, where neural networks with billions of parameters can generate shockingly realistic simulations of phenomena, from protein folding to entire virtual worlds. Some theorists speculate that our universe could operate on similar principles, with its physical laws emerging from an unimaginably complex optimization process. Just as a trained AI learns to minimize errors in its predictions, the fundamental constants of nature, the speed of light, the strength of gravity, might represent the most stable configuration for this cosmic network to process information efficiently. The implications collide head-on with quantum gravity research. In loop quantum gravity, spacetime is woven from tiny, indivisible loops, a granular structure that aligns suspiciously well with neural network models. Even black holes, those enigmatic spacetime warps, start to make new sense under this paradigm. Their event horizons could function like bottleneck layers in a neural net, compressing and transforming information rather than destroying it. This perspective offers fresh hope for solving the black hole information paradox, suggesting that what falls into a singularity might not vanish but get reprocessed, like data fed into an unfathomably dense hidden layer. Of course, this isn't without controversy. Critics argue that calling the universe a neural network risks being just a metaphor dressed up in mathematical formalism. After all, saying spacetime computes isn't the same as proving it literally is a computer. Others counter that the math speaks for itself. The isomorphism between tensor network equations and gravitational physics is too precise to ignore. Perhaps most dizzying is the philosophical undercurrent. If the universe processes information like a neural net, does that imply some form of cosmic cognition? Not necessarily. The theory doesn't require consciousness, only computation. But it does suggest that reality, at its most fundamental level, might be less about particles and forces and more about relationships and data flow. We may not be living inside some alien supercomputer, but inside a self-organizing, self-referential system where the very act of existence is a kind of calculation unfolding at the scale of everything. Whether this framework ultimately holds or not, it represents a seismic shift in how we conceive of reality. The old Cartesian divide between mind and matter crumbles when the fabric of space itself starts to look like a thinking structure. What remains is a haunting question. If the universe computes, what is it trying to solve? What if the flow of time isn't just a one-way street, but a two-lane highway where the future can reach back and shape the past? The concept of a time-symmetric universe shatters our intuitive sense of causality, suggesting that events yet to happen might influence what we perceive as history. This isn't science fiction, it's a serious interpretation of quantum mechanics, one that rewrites the rules of cause and effect. Take the quantum delayed choice experiment, a twist on the classic double-slit setup that baffled even Einstein. Normally, particles like photons behave as waves when not observed, creating interference patterns, but collapse into definite particles when measured. But what if you wait until after the particle has passed through the slits to decide whether to measure it? Astonishingly, the results show the particle's past behavior changes retroactively, as if future observations reach backward in time to dictate whether it acted as a wave or particle. It's like a detective altering a crime scene by the mere act of deciding to investigate it. John Wheeler, who proposed this experiment in the 1970s, saw it as evidence that reality isn't fixed until observed, even if that observation happens too late. The transactional interpretation of quantum mechanics proposed by Ruth Kastner takes this further. It imagines quantum events as handshakes between past and future, where offer waves from the present collide with confirmation waves from the future to create measurable outcomes. Picture throwing a ball in a room with two doors. The ball only goes through one door because the other door will be locked in the future, sending a wave of influence backward to steer the ball's path. This isn't just philosophical musing, it mathematically resolves the infamous measurement problem by eliminating the need for observers to collapse wave functions. The universe, in this view, is a vast negotiation across time, with every event requiring consensus from both past and future. Critics argue retrocausality introduces needless complexity, but supporters counter that it elegantly explains quantum weirdness without invoking parallel universes or consciousness-driven collapse. It also dovetails with recent experiments in quantum entanglement, where particles instantaneously influence each other regardless of distance. If time symmetry holds, their connection might not be faster than light, just a causal loop where future measurements set up the entangled state in the past. The implications are profound. If the future can mold the past, free will takes on a surreal new dimension. Our choices today might be entangled with consequences we haven't yet encountered. And if time is truly bidirectional, the universe isn't unfolding, it's refolding, with every moment a midpoint between what was and what will be. Whether this theory withstands scrutiny or not, one thing's clear: time, that steady arrow we thought we understood, might be the most cunning illusion of all. What if the universe isn't just described by mathematics, but is mathematics? Physicist Max Tegmark's mathematical universe hypothesis takes this radical idea to its logical extreme, proposing that reality isn't merely governed by numbers and equations, but is fundamentally made of them. Imagine peeling back the layers of the cosmos, past atoms and quarks, past space-time itself, until you're left with nothing but pure, abstract mathematical structure. In this view, the moon isn't a rocky sphere orbiting Earth. It's a specific solution to a differential equation, a knot of relationships in an eternal numerical tapestry. This isn't as alien as it sounds. The Pythagoreans of ancient Greece first whispered that all is number, hearing music in the orbits of planets and harmony in the ratios of geometry. Centuries later, Galileo declared nature's grand book was written in the language of mathematics. But Tegmark goes further. If a theory perfectly predicts observations without any physical baggage, no stuff, just equations, then maybe the baggage was never there to begin with. Think of a video game. The world feels real to the characters, but underneath, it's just code executing on silicon. Similarly, our universe might be a mathematical object, running on the barest framework of logic, with particles and forces as emergent properties, like shadows cast by deeper numerical symmetries. The implications for the multiverse are staggering. If reality is math, then every self-consistent mathematical structure, every possible set of equations, could describe a real universe somewhere in the multiverse. Some might have 4 spatial dimensions, others with time that flows backward, or with laws so alien that physics as we know it wouldn't apply. Tegmark calls this the level Roman 4 multiverse, a realm not just of alternate histories or bubble universes, but of every conceivable mathematical possibility. It's a dizzying thought. The universe where 2 + 2 = 5 might exist not because the math is wrong, but because that universe's math defines a different kind of 5. But where does consciousness fit in? If reality is pure math, how do subjective experiences, the taste of coffee, the sting of pain, emerge from cold equations? Some theorists, like neuroscientist Giulio Tononi, suggest consciousness itself might be a mathematical property, a pattern of integrated information that arises when a system reaches sufficient complexity. Others argue this reduces the richness of experience to mere computation, like mistaking a sonnet for its ASCII code. The puzzle echoes the hard problem of consciousness. Why does any of this feel like something at all? Critics dismiss the mathematical universe as untestable metaphysics, a sleek philosophy with no experimental hook. Yet Tegmark counters that it makes concrete predictions. If true, the ultimate theory of everything shouldn't contain any arbitrary physical constants, just pure structure. And if future physicists discover that deeper layers of reality keep revealing simpler, more beautiful math, it could hint that we're glimpsing the universe's true substrate. Until then, the hypothesis remains a profound thought experiment, blurring the line between physics and philosophy, between discovery and invention. Here's the haunting beauty of it all. If Tegmark is right, then mathematicians aren't just explorers uncovering truths. They're architects assembling new worlds with every proof. And somewhere in the infinite lattice of mathematical possibility, another version of this video might be unfolding in a universe where the script wrote itself. What if gravity isn't the universe's primary architect, but just one player in a far grander cosmic symphony? Nobel Prize-winning physicist Hans Alfvén dared to flip the script with his plasma universe theory, painting a cosmos where electromagnetic forces, not invisible dark matter, shape the dance of galaxies. Picture space not as a near-perfect vacuum, but as a seething ocean of ionized gas, threaded with colossal electric currents that sculpt matter into filaments and whirlpools. This is a universe where lightning isn't confined to storm clouds. It stretches between stars, galaxies, even clusters, orchestrating structures with forces a trillion times stronger than gravity. At the heart of Alfvén's vision are Birkeland currents, twisting rivers of charged particles named after their discoverer, Christian Birkeland, who first documented their earthly form as the auroras. But in Alfvén's cosmos, these currents operate on galactic scales, winding through space like cosmic serpents, pulling plasma into spinning disks and spiral arms. When two such currents intertwine, their magnetic fields pinch the plasma between them, compressing it into stars and galaxies without needing dark matter's gravitational crutch. It's a process you can recreate in a lab. Pass electricity through a plasma chamber, and watch miniature galaxies emerge, complete with glowing arms and central bulges, a scaled-down echo of nature's grand design. This challenges mainstream cosmology on its own turf. Take galaxy rotation curves. Astronomers observe stars orbiting galactic cores far faster than visible matter can explain. The standard fix: invoke dark matter's invisible halo. But plasma cosmology offers an alternative. The galaxies themselves might be immersed in vast, diffuse currents of ionized gas, their electromagnetic interactions providing the extra pull. Similarly, the universe's colossal web of galaxy clusters threaded along shimmering filaments might not trace dark matter's gravitational scaffold, but the branching paths of these universe-spanning currents, like frost spreading along a windowpane's cracks. Yet the plasma universe faces its own hurdles. Critics argue that while electromagnetic forces dominate in labs and stellar atmospheres, the near-perfect neutrality of interstellar and intergalactic space should cancel out large-scale electric fields. Alfvén countered with double layers, a thin, insulating sheaths where charges separate violently, allowing currents to flow across vast distances without dissipating. These cosmic capacitors could store energy like batteries, discharging in titanic flares that rearrange entire galactic neighborhoods. Some point to the mysterious radio loops, spanning thousands of light-years, potential remnants of such explosions, as smoking guns for this electrified cosmos. The debate crystallizes in the cosmic microwave background, the afterglow of the Big Bang. Mainstream models attribute its subtle fluctuations to quantum seeds magnified by inflation, but plasma cosmologists propose an alternative. Those patterns might be scars from primordial plasma instabilities, frozen into the sky when the universe cooled enough for atoms to form. It's a clash of paradigms with no easy resolution, yet experiments like the Sapphire Project are now testing plasma-based star formation in vacuum chambers, yielding structures eerily reminiscent of Hubble's deep field images. Whether the plasma universe ultimately displaces dark matter or simply enriches our understanding, it reminds us that the cosmos might be far more electrifying than we thought. After all, if 99% of the visible universe is plasma, maybe we've been telling gravity's story while ignoring the electric currents humming through the dark. What if the universe's deepest secrets aren't written in the language of physics, but in the syntax of quantum error correction? This cutting-edge theory reimagines space-time itself as a cosmic quantum computer, constantly running error-checking protocols to keep reality from glitching into chaos. Imagine your phone's autocorrect but scaled up to galactic proportions. Every particle interaction, every gravitational ripple, might be part of an unfathomably vast computation designed to preserve cosmic coherence. At the heart of this idea lies holographic error correction, a mathematical framework where the universe's three-dimensional information is redundantly encoded on a two-dimensional boundary, like a cosmic backup drive, ensuring no data gets lost in the void. The spark for this radical view came from an unexpected marriage. Quantum computing and the AD/CFT correspondence, a conjecture linking gravity in higher dimensions to quantum field theories on lower dimensional surfaces. Researchers noticed that the equations governing quantum error-correcting codes bore a striking resemblance to those describing how black holes preserve information on their event horizons. In both cases, information isn't stored where it appears to be. Just as a quantum computer spreads data across entangled qubits to protect against errors, a black hole might smear information across its horizon, encoding it in subtle quantum correlations that only make sense when viewed from the outside. This isn't just analogy, it's mathematical isomorphism, suggesting space-time itself might be a kind of error-correcting code maintaining cosmic coherence. Take the black hole information paradox. When matter falls into a singularity, classical physics says it's gone forever, but quantum mechanics forbids such irreversible information loss. Holographic error correction offers an elegant solution. The information isn't destroyed, it's scrambled and distributed across the black hole's surface like a cosmic rayed array. Even as the interior evaporates via Hawking radiation, the horizon's quantum code ensures every bit of data can theoretically be reconstructed, preserving the universe's quantum rulebook. It's as if black holes aren't cosmic shredders but ultra-secure cloud servers, encrypting information in ways we're only beginning to decipher. This framework also reshapes how we think about spacetime's fabric. In ordinary computing, error correction requires redundancy, extra bits to detect and fix mistakes. The universe might operate similarly, with its apparent volume emerging from overlapping quantum correlations at the boundary. Picture a hologram where every point on the 2D surface connects to multiple points in the 3D projection, creating a web of entanglement so dense it conjures the illusion of depth. Disrupt one thread and others compensate, maintaining stability like a cosmic game of Jenga where the tower never falls. This could explain why spacetime seems smooth and continuous despite being fundamentally quantum, its nature's way of error-proofing reality against quantum decoherence. Critics argue this conflates metaphor with mechanism. Just because reality's math resembles error correction doesn't mean the universe is literally computing. Yet experiments might soon test these ideas. Quantum gravity researchers are designing tabletop simulations using entangled qubits to mimic holographic encoding, watching for telltale signatures of emergent spacetime. Others probe the cosmic microwave background for anomalies that could reveal the universe's underlying code rate, how much redundancy it deploys to stay error-free. The most mind-bending implication: if the universe is a quantum error-correcting code, then glitches, tiny deviations from perfect coherence, might occasionally slip through. Some theorists speculate that dark energy could be such a glitch, a cumulative correction overflow stretching spacetime itself. Others wonder if quantum fluctuations in the vacuum are the code's background noise, the universe quietly debugging itself at Planck-scale resolutions. Whether the theory holds or not, it transforms our view of reality from a static stage to an active computation, one where every star, every atom, is a line in the cosmos's unfathomable source code, running checksums against the void. What if every galaxy, every star, every swirling nebula was just an electron in an atom so vast our entire universe fits inside it? This mind-stretching idea that the cosmos might resemble a single, unimaginably large atom has danced at the edges of physics for nearly a century. It begins with a curious pattern. The ratios of fundamental constants in nature keep spitting out eerily similar numbers, as if the universe's blueprint were echoing across vastly different scales. Take the ratio of the electromagnetic force to gravity between two protons, roughly 10 to the 39th power. Now compare that to the number of atoms in the observable universe, or the ratio of the universe's size to a proton's radius. Those same colossal digits keep appearing like cosmic breadcrumbs, hinting at a hidden connection between the microscopic and the galactic. Astrophysicist Arthur Eddington was among the first to chase these numerical ghosts. His fundamental theory proposed that the universe's constants weren't arbitrary but locked in a mathematical harmony reflecting deeper symmetries. He saw the universe as a self-referential structure where the very act of observation tied the large to the small. Imagine an electron orbiting an atomic nucleus. Now zoom way out until that electron's path becomes the orbit of a planet, or even a galaxy around a cosmic center. Eddington's vision suggested that quantum mechanics and cosmology might be two sides of the same coin, with the universe's expansion mirroring the probabilistic dance of subatomic particles. Modern physics breathes new life into this audacious idea through unified field theories. Some string theory models describe particles as vibrating loops where the notes they play determine their properties. At cosmic scales, these vibrations might translate to the rhythmic clustering of galaxies along filaments, like harmonics resonating across spacetime. Even black holes get a strange new role under this lens. Their event horizons could act like atomic shells, trapping energy in discrete levels akin to electron orbitals. The math reveals haunting parallels. Just as electrons occupy quantized energy states, galaxies might be constrained by similar cosmic quantization rules, their distribution not random but following a grand, unseen pattern. But the most tantalizing evidence comes from large-scale structure surveys. When astronomers map millions of galaxies, they don't find a uniform scatter but a web-like architecture with vast voids and dense clusters. Strikingly, these formations resemble probability clouds in atomic orbitals, regions where electrons are likely to be found. Could the universe's large-scale structure be a scaled-up version of quantum probability? Some theorists propose that dark energy, the mysterious force accelerating cosmic expansion, might even play the role of the atomic nucleus's positive charge, subtly shaping the cosmos's orbital geometry through repulsive gravity. Critics argue these parallels are just numerical coincidences, cosmic Rorschach tests where we're projecting patterns onto randomness. Yet the persistence of these ratios across space, time, and discipline whispers of something deeper. Whether the universe truly is a giant atom or merely behaves like one, the idea shatters our intuition about scale, suggesting that the very large and the very small might be locked in a mirror dance we're only beginning to glimpse. And if that's true, then every star, every planet, every one of us might be part of an atomic structure so vast, its full shape lies forever beyond the horizon of our perception. What if our universe isn't just expanding, it's still exploding outward from the collapse of a black hole in apparent reality? This is the cosmic egg hypothesis, a theory that reshapes the Big Bang into something far stranger. Imagine a black hole in some higher dimensional universe, its matter crushed to infinite density at the singularity. But instead of vanishing into oblivion, that singularity becomes the seed for an entirely new spacetime, birthing our cosmos like a cosmic Russian doll. The idea hinges on a profound symmetry. The equations describing a collapsing star and an expanding universe are eerily similar, just running in opposite directions. At the heart of this theory lies conformal mapping, a mathematical trick that lets physicists rescale dimensions without losing essential relationships. When applied to black hole interiors, these transformations reveal that what looks like a crushing singularity from the outside could, from another perspective, resemble an inflationary Big Bang. It's as if the event horizon acts like a cosmic funhouse mirror, bending the rules so completely that collapse flips into expansion. This isn't just abstract math, it's supported by the behavior of entropy. Black holes don't just trap matter, they maximize disorder. and our universe's own low entropy beginnings align suspiciously well with the thermodynamic aftermath of a singularity's rebound. Observational tests might sound impossible, but clues could lurk in the cosmic microwave background. If our universe emerged from a black hole, the parent cosmos might have imprinted faint, swirling patterns, B-mode polarizations, left by primordial gravitational waves. These could differ subtly from those predicted by standard inflation, offering a smoking gun for the cosmic egg. Another hint might come from dark matter. Some models suggest it could be remnants of the parent universe's physics, particles that slipped through the singularity like cosmic stowaways, invisible but for their gravitational pull. The implications are staggering. If true, every black hole in our universe could contain a fledgling cosmos, each with its own laws and constants, a fractal multiverse born from collapse. And somewhere beyond our cosmic horizon, the reality that birthed us might still exist, its physicists peering into their own black holes, wondering if anything lies within. Whether this theory holds or not, it rewrites the universe's origin story not as a singular beginning, but as a link in an infinite chain of cosmic metamorphosis. What if the digital universe we've been debating isn't running on some alien supercomputer, but on the unfathomable processing power of a black hole? This mind-bending synthesis of simulation theory and black hole cosmology suggests that advanced civilizations might not just create ancestor simulations, they could harness singularities as nature's ultimate quantum processors. Picture this: a society billions of years ahead of us stumbles upon the perfect computational substrate, not silicon or qubits, but the space-time warping depths of a black hole's event horizon, where information gets scrambled, stretched, and preserved in ways that make conventional computing look like an abacus. The logic begins with black holes' eerie resemblance to computers. Just as a laptop uses energy to flip bits, a black hole processes information by encoding it on its horizon, a principle holography made famous. But here's where it gets wild. Leonard Susskind and Gerard T. Hooft showed that all the quantum information swallowed by a singularity isn't lost. It's smeared across the horizon's surface like cosmic Arium, with each Planck-sized pixel storing data. For an advanced civilization, this isn't just physics, it's an engineering roadmap. By carefully feeding matter into a black hole, they could theoretically program it, using infalling particles as input bits and Hawking radiation as output. The singularity itself would act as the processor, crunching calculations through spacetime's violent geometry. Now layer on simulation theory. If such a civilization wanted to run ultra-realistic ancestor simulations, Nick Bostrom's hypothesized parent reality, they'd need unimaginable computational resources. Ordinary quantum computers might handle toy universes, but simulating every quark in a cosmos demands energy densities only black holes can provide. The event horizon's holographic properties offer a cheat code. Instead of simulating every atom, the system could render only what's observed, like a video game optimizing graphics for the player's viewpoint. This resolves the frame rate problem: how to simulate a universe in real time without infinite lag. A black hole's time dilation near its horizon means billions of simulated years could pass internally while barely a second ticks by outside. To the simulated beings inside, reality would feel seamless, never suspecting their universe runs on borrowed spacetime. But the real kicker: this might already be happening with us as the simulation. If black holes naturally encode information holographically, our universe could be an emergent simulation running on the horizon of a parent black hole in a higher dimensional cosmos. The math even hints at eerie parallels. The universe's observed information content matches what's theoretically storable on a horizon-sized shell, while dark energy's acceleration could reflect computational resource limits. Some theorists speculate that quantum indeterminacy, the randomness at reality's core, isn't a bug but a feature, a sign of the underlying processor's finite resolution. Critics argue this conflates metaphor with mechanism. Black holes aren't literally GPUs, yet the circumstantial evidence is haunting. Why does the universe's information capacity so neatly align with holographic bounds? Why do black holes and quantum computers both rely on entanglement and non-locality? Whether the theory holds or not, it forces a profound rethink of reality's infrastructure. Perhaps we're not just in a black hole, we might be the output of its unknowable calculations, a cosmic simulation running on the darkest, densest hardware imaginable. Imagine peeling back the layers of reality until only a shimmering two-dimensional surface remains. A cosmic projector screen encoding every star, every galaxy, every fleeting thought in flickering quantum bits. This is the heart of the holographic universe theory refined through quantum information theory, where spacetime itself emerges from entangled qubits like a 3D mirage woven from a flatland of data. At the core of this revelation lies entanglement entropy, a measure of how quantum systems share information across invisible connections. When particles become entangled, their fates intertwine so deeply that measuring one instantly defines the other, no matter the distance. But here's the twist. This quantum glue doesn't just link particles, it might stitch together the very fabric of space. The Ryu-Takenogi formula offers a breathtaking bridge between these abstract quantum links and the geometry we perceive. Developed by Shinsei Ryu and Tadashi Takenogi, it mathematically proves that the entanglement between regions of space directly corresponds to the area of surfaces connecting them. Picture 2 points on a hologram's edge. The more quantum bits they share, the deeper the bridge between them in the projected three-dimensional world. This means the vast emptiness separating galaxies isn't truly empty, it's humming with entanglement, an invisible lattice of quantum relationships that literally defines the distance between objects. A black hole's event horizon exemplifies this perfectly. Its surface area isn't just a boundary but a measure of all the quantum information trapped inside, a ledger keeping track of every atom that ever crossed its threshold. How does this flat quantum code conjure up the richness of our 3D world? Think of a sand painting. From afar, you see intricate shapes and shadows, a face, a landscape, but up close, it's just grains on a flat surface. Similarly, quantum bits on a two-dimensional boundary might arrange themselves in patterns so complex that when viewed from within, they manifest as the depth and texture of spacetime. This isn't just metaphor. Simulations using tensor networks, mathematical models of entangled qubits, have successfully recreated features of general relativity, suggesting Einstein's curved spacetime could emerge from quantum correlations like a shadow puppet cast by deeper, dimensionless interactions. The implications rewrite cosmology's rulebook. If spacetime is emergent, then concepts like locality, the idea that objects are directly influenced only by their immediate surroundings, become illusions. Quantum entanglement already defies locality, with particles influencing each other instantaneously across light years. In a holographic universe, this spooky action at a distance might be the primal mechanism that knits space together, like threads in a tapestry we're only now learning to see. Even time's flow could be a side effect, a thermodynamic artifact of how quantum systems scramble information. Experiments with ultra-cold quantum gases have observed entanglement spreading in ways that mimic cosmic expansion, hinting that the universe's growth might be less about stretching space and more about information propagating through an invisible quantum network. Critics counter that holography remains untested at cosmic scales, but upcoming quantum gravity experiments aim to probe spacetime's pixelation. The holometer at Fermilab, for instance, hunts for Planck-scale jitter in laser beams, potential evidence of the universe's underlying code resolution. Others study black hole mergers for anomalies in gravitational waves that might reveal holographic pixelation near event horizons. Whether these efforts succeed or not, the quantum hologram theory has already shattered our intuition about reality's infrastructure, revealing a cosmos where the deepest truths aren't written in the stars, but in the silent conversations between quantum bits we're only beginning to decipher. What if every particle collision, every galactic rotation, and every fleeting thought is just a line of code in a cosmic program, one that's not just running but actively rewriting itself? Digital physics flips the script on reality, proposing that the universe isn't merely described by math but operates like a vast, self-updating algorithm. At the heart of this idea lies a radical shift. The laws of physics aren't static rules etched into the fabric of space, they're dynamic computations unfolding step by step, with each moment generating the next in an endless chain of cosmic recursion. Stephen Wolfram's work on cellular automata offers a stunning glimpse into how this might work. Picture a grid of squares, each black or white, following simple rules. A cell might flip its color based on the states of its neighbors. Run these rules iteratively, and from this minimal setup, intricate patterns emerge: spirals, fractals, even behaviors mimicking fluid dynamics or traffic flow. Wolfram's groundbreaking discovery was that some of these systems achieve computational universality. They can perform any calculation given the right initial conditions. Our universe, he argues, might be one such automaton, its apparent complexity arising from basic rules playing out across astronomical scales. It's like watching a chess game where the board is space-time, and every move advances the universe's state, except the rules themselves can evolve, adapting as the computation unfolds. This leads to the mind-bending concept of computational irreducibility. In most systems, you can predict outcomes by shortcutting the math. Think of calculating a rocket's trajectory without simulating every air molecule it encounters. But some processes, like Wolfram's automata, resist such shortcuts. The only way to know what happens is to run the program step by tedious step. If the universe operates this way, it would explain why quantum events seem fundamentally unpredictable. There's no equation to skip ahead because reality is the computation. Even more hauntingly, it implies that free will might not be an illusion but an inherent feature of a universe where the future isn't preordained, it's computed on the fly. Critics argue this reduces physics to metaphor, mistaking patterns for mechanisms. Yet digital physics finds eerie support in quantum information theory, where particles behave like qubits processing data, and black holes seem to obey thermodynamic limits akin to a computer's memory constraints. Even the speed of light might reflect the universe's processor clock rate, a limit on how fast information can propagate through the cosmic circuit, the most provocative implication. If the universe is an algorithm, it might contain instructions for self-replication. Just as a virus copies its code into host cells, the cosmos could embed the means to spawn new universes, perhaps inside black holes, where singularities trigger new computational cycles. This turns cosmology into a kind of cosmic computer science, where the multiverse isn't just a collection of worlds but a branching network of running simulations, each tweaking its initial parameters in an endless experiment. Whether you find this exhilarating or unsettling, one thing's clear. In a self-replicating algorithmic universe, reality isn't just written in code, it is code endlessly compiling itself into existence. What if galaxies aren't just islands of stars but neurons in a cosmic brain, firing across unimaginable distances? The structure of the universe's large-scale web filaments of galaxies stretching billions of light-years, connected at nodes like synaptic junctions, bears an uncanny resemblance to the neural networks inside our own skulls. Zoom out far enough, and the cosmic web's branching patterns mirror the brain's dendritic arbors so precisely that it's hard to dismiss as mere coincidence. This eerie similarity has birthed a provocative idea. The universe might not just look like a brain, it could function like one, processing information on scales so vast we're only beginning to glimpse the rules of its cosmic cognition. At the core of this theory lies a radical reimagining of spacetime's fabric. Just as neurons communicate via electrical pulses, galaxies might signal each other through gravitational waves or entangled quantum fields, their interactions weaving a dynamic network of cosmic computation. Physicist Dmitry Kirev's work on scale-free networks reveals that both brains and the universe obey similar mathematical principles. Both systems optimize for efficient information transfer while minimizing energy costs. In the brain, this creates small world networks where any two neurons connect through just a few steps. In the cosmos, galaxy clusters achieve the same efficiency. Proxima Centauri might be light years away, but gravitational interactions ensure no corner of the universe is truly isolated. It's as if nature has a favorite blueprint for complexity, recycling it from synapses to superclusters. The parallels deepen when examining how information propagates. Neural networks learn by adjusting synaptic weights, strengthening or weakening connections based on input. The universe, too, seems to rewire itself through dark matter's invisible scaffolding, where gravitational pull dictates which galactic filaments thrive and which fade. Some models even suggest that cosmic voids, the empty spaces between filaments, act like inhibitory neurons, dampening activity to maintain equilibrium. This isn't just metaphor. Simulations using neural network algorithms can reproduce the universe's large-scale structure with startling accuracy, hinting that the same underlying logic might govern both systems. Yet the theory faces fierce skepticism. Critics argue that resemblance isn't causation. Just because two systems look alike doesn't mean they operate alike. Galaxies don't process information in any meaningful sense. Their interactions are governed by gravity, not logic gates. Others caution against anthropocentrism. The human brain evolved to recognize patterns even where none exist. But proponents counter that dismissing the analogy outright ignores deeper questions. If the universe behaves as if it's computing, does the intent matter? Whether it's conscious or not, the cosmos might still function as a self-organizing information processor, with black holes acting like cosmic nodes crunching spacetime's data. Perhaps the most tantalizing question isn't whether the universe is a brain, but what this perspective reveals about reality's nature. If neural networks, both biological and artificial, can mimic cosmic structure, does that imply existence itself runs on some universal algorithm? Or are we simply glimpsing the fractal symmetry of a deeper, hidden order? Whether the analogy holds or not, one thing's certain: the universe's grand design keeps echoing patterns closer to home, as if whispering that the macrocosm and microcosm are far more alike than we ever dared to dream. What if every particle in the cosmos isn't a tiny dot, but a vibrating string, each oscillation a unique musical note in the grandest symphony imaginable? This is the breathtaking premise of string theory, where the universe isn't just governed by equations but composed of microscopic strings whose vibrations dictate everything from the mass of an electron to the gravity-bending starlight. Picture a cosmic violin with infinitely tiny strings, some vibrating gently to produce quarks, others thrumming intensely to create photons, all harmonizing across hidden dimensions we can't perceive. The universe wouldn't just have music, it would be music, a composition written in the language of spacetime itself. The origins of this idea trace back to the late 1960s, when physicist Gabriel Veneziano stumbled upon a mathematical formula describing the strong nuclear force, an equation that just happened to mirror the physics of vibrating strings. What began as a quirky analogy soon blossomed into a full-fledged framework for quantum gravity. Unlike point particles in traditional physics, strings, whether open-ended like threads or closed like loops, introduce a mesmerizing possibility. Their vibrations aren't random but quantized, meaning they can only oscillate at specific frequencies. Each allowed vibration corresponds to a distinct particle, much like how a guitar string only produces certain notes. The sound of one vibration might manifest as an electron, while another becomes a Higgs boson, transforming the standard model into a kind of cosmic sheet music. But strings need space to move far more than our familiar 3 dimensions. To reconcile their behavior with observed physics, string theory demands at least 6 extra dimensions, curled into shapes so tiny they evade detection. Think of these hidden dimensions as the universe's harmonics, the overtones you can't hear but that enrich the fundamental tone. Mathematicians call these shapes Calabi-Yau manifolds, intricate 6-dimensional geometries that might resemble fractal origami at scales a billionth of an atom. The particular way a Calabi-Yau manifold folds and twists would determine the vibrational modes of its strings, which in turn fixes the constants of nature in our visible dimensions. A slight change in this geometry might make electrons heavier or gravity stronger, as if tuning a cosmic instrument to a different key, the theory's boldest promise. Unification. Just as a single violin string can produce multiple notes, string theory aims to weave all fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, into a single vibrational framework. In this vision, particles aren't separate entities but different expressions of the same underlying strings, much like C# and E are just 2 states of the same guitar string. Even spacetime itself might emerge from the tangled symphony of strings interacting, their collective vibrations creating the illusion of a smooth, continuous fabric. Yet for all its elegance, string theory remains controversial. The string's minuscule scale makes direct testing impossible with current technology, and the math often demands supersymmetry, a hypothetical doubling of particles that colliders like the LHC haven't found. Some physicists argue this lack of falsifiability pushes string theory into metaphysics, while others see it as a victim of its own ambition, a theory so comprehensive it outpaces our ability to verify it. But whether strings ultimately describe reality or not, their legacy reshapes how we see the cosmos. The universe might not be a cold machine of cogs and gears, but a living, breathing composition, an eternal concerto where every atom sings and the laws of physics are just the rules of harmony. And if that's true, then the night sky isn't just a scattering of stars. It's a celestial score waiting to be deciphered. From holographic projections to black hole computers, vibrating strings to cosmic neural networks, these 30 theories don't just expand our understanding of reality. They shatter it entirely, revealing a universe far stranger, wilder, and more mysterious than we ever imagined. Whether spacetime is an illusion, consciousness is universal, or we're all flickering simulations in some unfathomable quantum processor, one thing's certain: the cosmos refuses to be boxed into simple explanations. These ideas aren't just science, they're invitations to wander the edges of human imagination, to question everything we think we know about existence itself. What's astonishing isn't just the breadth of these theories, but how they converge in their audacity. The holographic principle whispers that our 3D world might be a shadow cast by quantum code written on the universe's edge. Eternal inflation paints a multiverse where countless bubble universes bloom endlessly in an unseen void. And quantum mechanics, it suggests time itself might be a two-way street, with the future reaching back to shape the past. Even contradictions become poetic. The universe could be both a single, timeless mathematical object and a living, evolving network, pulsing with self-organizing complexity. Yet for all their differences, these theories share a single, humbling message: we've only scratched the surface. Every time we build a better telescope or a more powerful collider, reality peels back another layer, revealing deeper puzzles. The mysteries of dark matter, the enigma of consciousness, the paradoxes of quantum gravity, these aren't gaps in our knowledge, they're doorways, and standing at the threshold, we're left with more wonder than answers. So here's the real question: which of these theories grips you the most? Does the simulation hypothesis unsettle you, or does the cosmic web's resemblance to a brain ignite your curiosity? Maybe you're drawn to the elegance of string theory's vibrational universe, or the haunting beauty of Penrose's cyclic cosmology. Whatever it is, dive deeper. Debate it, question it, because the greatest gift of these mind-bending ideas isn't their conclusions, it's the conversations they spark, the curiosity they fuel, and the reminder that reality, in all its infinite strangeness, is always more dazzling than we dare to dream. The universe isn't just out there, it's here, in every question we ask, every theory we test, every night we spend staring at the stars and wondering. So keep wondering, the cosmos isn't done surprising us yet.